Lab 4 Oscillations. The purpose of today's video is to compare the predicted motion of an oscillating spring with an attached mass to the observed motion. To do so, we will gather data from VPython and Tracker. Next, we will plot the energy changes occurring in our system, including spring potential, spring kinetic, gravitational potential, and total energy. The main lab results we will see by the end of this video is 1. The predicted x and y positions of the spring are similar to the observed position, but not 100% accurate. And 2. We will see that by the energy principle, the total energy change is 0. The main physics ideas that are present in this experiment are Newton's second law, F net equals delta P over delta T. We also need the formulas for gravitational and spring force. Force of gravity is equal to mg, and force of spring is equal to negative k times L mag minus L naught times L hat. These two key formulas will lead us to calculate the net force acting on the spring. The next key formula that we'll be using is the energy principle. The energy principle states that the change in system energy is equal to work surroundings plus heat. In this case, we are assuming there's no heat being applied to the spring. Instead, we will calculate the change in system energy by summing the change in spring kinetic energy, spring potential energy, and gravitational potential energy. Similar to every other lab, we will need to use the velocity update and position update formulas to track the position of the spring. The models that will be used to support these formulas include a position time graph and an energy time graph. In this experiment, I downloaded a video of a professor releasing a spring with an attached mass from rest. In Tracker, I set the mass of the system to 0.402 kilograms and calibrated the elongated spring to be 0.7 meters in the negative y direction. The initial position of the spring upon release was negative 0.118 meters in the x direction and negative 0.627 meters in the y direction. The initial velocity was 0 meters per second because the spring started from rest at time t equals 0, and the experiment ran for 9.497 seconds. The system in this experiment includes mass, spring, and earth, while the surroundings is nothing. Because there are no surroundings, we can say the work done by the surroundings on the system is 0. Likewise, this means the change in total energy of the system must be 0 by the energy principle. In the beginning of the code, I set the initial conditions, which were the same as outlined previously: ball mass, initial position, and initial velocity, and delta t, which I set to 0.095 seconds. Next, I set g to 9.8 meters per second squared and the spring constant k to 6.83. The spring constant was determined by the oscillation period formula shown at the top. Solving for k returns the spring constant, but we also have an unknown variable t. To get an accurate estimate for t, we took the average oscillation period of the graph over 3 loops and used this value as our final t. Next, we found the relaxed spring length by solving for L naught in the spring force equation. Using the same spring force equation, I computed S, the change in length of the spring, and I went ahead and calculated the system energies. The net force was set to 0 because the energy principle says all energy is conserved. Moving on to the while loop in my code, I once again set the initial energies for the spring and earth so that I can iteratively update them throughout the while loop. In the next few lines, I converted my spring force and gravitational force into vectors, and then updated my velocity, position, and spring displacement using the net force. Finally, I calculated the change in kinetic and change in potential energies by subtracting the final values and the initial values. When comparing the experimental data of Tracker and predicted data of VPython, we can see that overall, the graphs share the same trend and have similar periods of oscillation. However, when we look more closely at graph 1 on the left, the experiment curve slowly diverges from the predicted periods of oscillation. In graph 2 on the right, the experiment curve has amplitudes smaller than the predicted model. So is the energy principle satisfied? The answer is yes. There are no surroundings in this experiment, so we can say that the system is fully isolated. The energy principle says that all energy is conserved, and we can see this because the total energy change of the system, represented by the orange line, is at constant 0. Likewise, spring potential in green and gravitational potential in red are inversely related, so they have a destructive interference when added together. Kinetic energy oscillates too, but is much weaker than the potential energies. As mentioned earlier, we found the average oscillation period t to be 1.524 seconds, but this is because we use the y direction as our estimate. If we use the x direction instead, we can see that the average oscillation period is now 1.633 seconds. The difference between these two times is merely a tenth of a second, but depending on the value you choose to use, the difference in oscillation periods can cause a large deviation in the glow script prediction. A faster oscillation period, like the one in the y direction we used, means there will be a lower k constant, which throws off the rest of the data. In conclusion, taking everything to be our system means the change in total energy must be 0, according to the energy principle, and this is held true in this experiment. We also see that spring potential and gravitational potential energies are inversely related. Some potential sources of error might include the accidental misplacement of dots when tracking the mass. Friction drag and the weight of the spring were not accounted for in the glow strip code, so this explains why the graphs are not completely accurate. The initial position measured by the professor, which I calibrated to be 0.77 meters, might have been off. And finally, as mentioned before, the spring constant K isn't completely accurate because we found the oscillation period as an average of the y direction.